All right, so we're going to go ahead and take a look at where we left off yesterday with probability. We kind of finished on this slide right here, and this slide was looking at how many desirable outcomes for the situation of if we toss a coin three times, and what's the probability it's going to land on heads exactly two times, right? So yesterday we sort of brute forced this calculation, and I wanted you guys to get an understanding of sort of how this is derived. And then in the assignment yesterday, if you did this part of the assignment, you probably realized that there was some tedium involved. In other words, it got a little tedious when it came to, six different trials and having to draw this tree out and calculating the probability there. So if you got a little frustrated with that process, I don't blame you. I just wanted you to see how it worked, sort of doing it by hand, so you understood. Now, what we're going to see in this presentation today is that there's actually a way to calculate this with a formula, which is much better. As you can imagine, if you started asking questions about this sort of thing with much larger numbers, it becomes very impractical to sort of draw this tree every time. So, in 1,000 tosses, what are the probability that I'm going to get heads 400 times? You just couldn't do this by hand. So how is it that we're going to be able to do this with a formula? Well, moving on, it's called the binomial process. And before we actually get into how this process works, you have to understand a few things about it. And that is, it only works for situations where the trial has two possible outcomes, yes or no, on, off, right, wrong, positive, negative, whatever it might be. So that's very important. So a heads or tails, for heads or tails, binomial process works, but this wouldn't work for some other processes. So just keep that in mind. If there's more than two outcomes, then this equation doesn't apply. It's also important to understand that these two outcomes have to be independent. So tossing a coin does not affect future tosses. In other words, just because I flipped heads three times in a row doesn't mean that next time I'm any more likely to get tails. I'm equally likely to get heads on the fifth toss as I was on the previous four. So the past events do not influence the future tosses. Everything's truly random. So, before we get into it, I do want to remind you guys of what a factorial is. You may have learned this in algebra, but it may have been a while. So, factorial of n, the number n, the integer n, is just that number times every subsequent number below it, every subsequent integer below it, down to 1. So 1 factorial is just 1 because there are no integers below it, but you can see the other examples. So we'll just skip to 5. 5 factorial would just be 5 times 4 times 3 times 2 times 1, which comes out to 120. And that's important because you're going to see factorials in our formula coming right up. So here's the big slide of the presentation for today, and that is the Bernoulli process. And this is what would allow you to calculate the probability of, say, getting exactly 4 heads out of 6 tosses or whatever. So if you have a question of probability, this formula can allow you to calculate it instead of having to draw those trees like we saw. So with that in mind, let's just examine the formula. It is right up here. The blue formula is what I want us to focus on. And it's the probability of x is equal to n factorial over x factorial times n minus x factorial times p to the x times q to the n minus x. So obviously not a super simple formula, but it is something that we should be able to wrap our heads around as soon as we understand what these terms mean, right? So that's the biggest part of this, is understanding what every term here represents. So, well, what is n? N factorial is on top there. Well, n is simply the number of trials, okay? So if I'm going to toss a coin 6 times, then I'm going to have n is equal to 6. X is the number of times for a specific outcome. So that's where I say, okay, well, I want 4 heads, right? So if I'm looking for that specific outcome, that's what X is. And then, of course, once we've defined N and X, then N minus X simply becomes the difference between the two, which is very easy. And then we have P, which is the probability of success on a single trial, and Q, which is the probability of failure on a single trial. Now, since this is a binomial process, meaning there are only 2 outcomes, it's important to understand that P and Q will always add up to 1, because the probability has to always total to 1. So if P is 0.3, then Q has to be 0.7. Or if P is 0.2, then Q has to be 0.8. But in any case, the point is once you have defined all of those terms, then you can kind of try to fill it out for a given problem and answer that question. So we're going to see an example here on the next slide. So it says here, what is the probability of tossing a coin 3 times and it landing on heads up 2 times? So this was the example we looked at before, and the first time we did it, we sort of brute forced it with a little tree where we drew it out and sort of analyzed it. But here we can apply it to actually calculate the answer directly. So that's what we're going to do. We have our equation where n factorial times p to the x times q to the n minus x over x factorial times n to the minus x factorial. Now, I do want to point out real quick before we move on that this is in fact the exact same formula as what we saw in the previous slide, so let's look. All they're doing is taking these two terms right here and moving them in the numerator right next to n. So I'm not exactly sure why they wrote it 2 different ways here, but they did. So I just want to make sure you understand it's the same formula, no changes really. So let's just sort of think about this for a moment. Well, what is n? As we said before, n is the number of trials. So what is the probability of tossing a coin 3 times and it landing heads up 2 times? So n is going to be 3 for this problem because the number of trials is 3. P is the probability of success, and Q is the probability of failure. So what's the odds I'm going to get heads? Well, it's 50%, 0.5. And Q, the probability of failure, is the same. It is also 50%. So I'm going to see N here being 3, P being 0.5, and Q being 0.5. Now what about X? Well, X was the number of times for a specific outcome within N trials. So I want heads 2 times, so X is going to be 2. And then of course N minus X will be 3 minus 2. So if we go ahead and take a look at that, this is exactly what we see. We see the calculation as we expect it to be. Let's just make sure of that. 3 is n, and so what you see here is 3 factorial, 3 times 2 times 1. P is the probability, which we said is 0.5, and there it is. And x, of course, we defined as 2 times, so x is 2, so p gets raised to the second power. Q gets raised to the n minus x, which is 3 minus 2, which is 1. Q is 0.5. You can kind of see it all work out. It does take some practice to understand exactly how to plug all this information in. So don't be stunned if you struggle a little bit the first few times. That's totally fine. With that said, you obviously want to use a calculator to see how this probability shakes out, but it's not too bad. And of course, we get the answer we would expect, which was the answer from our previous slide when we did it sort of the brute force method of 37.5% probability that we're going to get heads 2 times, okay? So a little more than a third of the time we conduct this trial, we're going to get heads twice. Okay, so the law of large numbers is the general idea that there's an average out there, right? So you may have heard regression to the mean, and that's the idea that the more times you try something, the more trials you have, the more likely that outcome is going to be what's expected, okay? So if you have only 5 tries to toss a coin, well, you have to end up with more heads than tails, or you have to end up with more tails than heads. You can't have them equal, right? So for example, in trial 1 here, when we toss the coin 5 times, obviously it's impossible to get our theoretical probability for that circumstance. Now, if I up the number of trials to say 500, then obviously my probability is going to shift much more heavily towards that 50% probability now. So it's important to understand that the higher the number of trials, the more likely you get close to that theoretical probability. And that's all this slide is telling us here, is that in general, the law of large numbers, sometimes called sort of like regression to the mean, means that things are going to shake out to what we expect them to over time as the number of trials increases. All right, so about probability and multiplication. If you have independent events occurring simultaneously, then, and you want to say, okay, so what's the probability that these two things are going to happen at the same time? Now keep in mind these are independent, so one does not affect the other. Then the probability of those two events occurring simultaneously will simply be the product of the individual probabilities, okay? So if A and B are independent events, then the probability of A and B occurring simultaneously is simply the product of those two probabilities, okay? And so, here we go. Well, that's pretty much it. I was thinking of an example. I guess you could say, this would be sort of not simultaneously, but it would be like, yeah, no, we could do it simultaneous. So say I have a die and you have a die, and we're gonna roll our dice, right? And I say, hey, I wonder what the probability we both roll sixes is gonna be, right? Well, I have a 1 in 6 chance of getting a 6, and you also have a 1 in 6 chance of getting a 6. So the probability that we both roll the same number, that is 6 specifically, is 1 in 6 times 1 in 6, which will be 1 in 36. So the probability would be 1 over 36. So we'd only expect to both of us roll a 6 1 out of 36 tries. So it might take quite a while before we actually do that, is the idea. Okay, it says, what is the probability of rolling 4 on a single die? Well, we just have to look at the number of desirable outcomes and the number of possible outcomes to figure that out. And we know that the die has 6 sides, so there's one desirable outcome, 4, and a possible outcome might be 6, right? So we have a 1 in 6 chance, and this is the same basic example that we saw, that I gave on the previous slide. It's just this time the number is a 4, and then a 1. So if we have 2 dice, one of them is a 4, one of them is a 1. Well, they each have a 1 in 6 chance of, that number coming up. So the possibility that if I roll 2 dice, or sequential rolls, right, then what is the odds that I'm going to roll a 4 and then a 1? Well, that is going to be the product of those two probabilities, which is 1 over 6 times 1 over 6, which comes out to 1 in 36, or about 2.78, a little less than 3%. Okay? So, let's see here. Independent events occurring individually. Oh yeah, I guess we could do this one. I was trying to remember if I wanted to include this or not. So yes, okay. So if the independent events, if you're wondering about the probability that those independent events will occur individually, right? Then you simply add up the sum of the individual probabilities, okay? So if A and B are mutually exclusive, okay, then the probability of A or B occurring is the sum of the two probabilities. So let me try to put some context to that right there, okay? What this slide is saying is, what are the odds that I roll either a 1 or a 4 in a single dice roll? Okay, what are the odds I roll either a 1 or a 4? Well, they're mutually exclusive, meaning I can't roll a 4 and a 1, right? So I can only roll a 4 or a 1. So they are mutually exclusive. And then the total probability of me rolling either a 4 or a 1 would be the sum of the individual probabilities. Now, the odds of me rolling a 4 is 1 over 6, and the odds of me rolling a 1 is 1 over 6. So the total probability that I'll roll either a 4 or a 1 is the sum of those two numbers, 1/6 plus 1/6, which comes out to 2/6 or 1/3, okay? So that's what we're looking at right here. So this is pretty much exactly what I was just saying. Again, if I have a probability of 1/6 of rolling a 4 and a probability of 1/6 of rolling a 1, then what are the odds in a single roll of the die that I roll a 4 or a 1? It's going to be the sum of those two probabilities, which is about a 1/3 chance, right? So I need a 4 or a 1. What are the odds I'm going to be successful? 33% are the odds that I'm going to be successful, right? And then this is our last slide for the lesson here. If I have independent events and I want to know what the probability of something not happening is, well, then it's just 1 minus the probability that it will occur. So a very simple example here would be, let's take that 4 again. What are the odds I roll a 4? Well, I know the odds I roll a 4 are 1 in 6, right? 1 out of 6 times I'm going to get a 4. Well, what are the odds I don't roll a 4? Well, it's the difference between 1 and 1/6. So the probability that I'm going to roll anything but a 4 will be 1 minus 1/6, which will be 5/6. Okay, and so that's what we see right here, and so it's about an 83.33%. Okay, so that's it for today in terms of direct instruction from the PowerPoint. The other information I'm going to provide you with is related to getting your assignment done, and I'm going to make some things a bit easier on you. So I want to kind of give you a little bit of information so you understand how to do the rest of the assignment. The first piece of good news is I don't want you to do number 5. I just want you to see number 5. So this is the answer to number 5. I was looking at this and I'm thinking to myself, this is not really a valuable use for your time. It's kind of tedious. And so instead of having you do all of this, I figured I'd just show it to you and make sure you understood what's going on here. So let's just examine it. It says create a histogram representing the summation possibilities of rolling 2 dice simultaneously, right? And then they make a note. Note that rolling a 2 and a 3 is not the same as rolling a 3 and a 2. So if I roll a 3 and a 2 and a 2 and a 3, that counts as 2 different ways that I can get 5 as an example. So how many different ways can I get a sum of 2 between 2 dice? Well, if I'm going to roll 2 dice and I want 2, they both have to be 1, and that's the only way of doing it. So my sum is 2, my event would be rolling a 1 and a 1, and the frequency of that would be, well, there's only one way to do it, okay? So it has to be 1. Now, what if I wanted to look at how many ways I can roll a 3? Keeping in mind that the maximum number, of course, between 2 dice is all the way up to 12, because I can roll 6 and 6. And of course, we see there's only one way to do that, right? So you can kind of get an idea of what's going on here. In order to roll a 3, I can either roll a 1 and a 2 or a 2 and a 1. So that's 2 different ways that I can get 3. To get a 4, I can roll a 1 and a 3 and a 1, or I can roll a 2 and a 2. And so that would be a frequency of 3, and then you can go on, and it kind of goes through all of them, and you can kind of see that we have, well, it kind of looks like a bell curve. In fact, if you turn this on its side, with this right here being the bottom, you have a bell curve. And so this is why the number 7 is rather common in gambling, because it actually happens to be the most common number in terms of the frequency for somebody to say win at craps or whatever, right? Now, of course, it's the most common outcome for the sum of 2 dice, but that doesn't mean that the odds are in your favor. If you look here, the sum of the numbers is 7, and the frequency of that is 6, but that frequency is only a small fraction of the total being 36. So really, you're looking at a 1 in 6 chance, which is only about 17% of rolling a 7. So, they tell you in Vegas the house always wins, and, well, it's probably better to say the house wins 83% of the time in craps, but you get the general idea. So hopefully this histogram makes some sense for you, and again, I was looking at it and I was just thinking this isn't a very good use of your time, so I'd rather you just see it to understand what's going on here. And this will also help make your understanding of what you're supposed to do with the rest of the assignment more clear, I think. So as you get through the assignment, you're going to come to this chart here, and this is an example chart that I filled out up to 20 here. Now, I think you have to go up through 50, so it's going to take you a bit longer, but in short, you're going to need 2 dice for this. Now, you have a couple of options. You either own 2 dice, and you can roll them, which is always fun, or if you really want to, you can go online and just say, online dice roller, and you can roll 2 6-sided die. And you need to do this 50 different times. And when you do, you're going to go ahead and record your results the way I've recorded my results here. So on die 1, for roll 1, I got a 6, and on die 2, I got a 3. So the total from those was 9. And on roll 2, I got a 4 and a 4, and the total was 8. And roll 3, a 1 and a 3, and the total was 4, and so forth. So you're going to fill out your chart by rolling these 2 dice 50 different times, and then you're going to record your totals. And then, of course, it's going to ask you questions about relative frequency, which is going to require you to add up some of your totals here. Examine how many times, for example, the number 10 appeared. So in my example here, I have 10 1, 2, 3 times. So my relative frequency for 10 would be 3 over 20. And so you're going to be answering some questions along those lines. I'm going to go ahead and end it here. Hopefully this gives you guys sort of a leg up on finishing the assignment. Good news, I'm not going to ask you to do the conclusion questions, so instead I'm just going to have you finish your procedures. And again, on number 5, I've already done it for you, so feel free to use this slide right here to sort of fill that out so you understand what that's all about. But in any case, I hope you guys found this clear and helpful. I'll be available, as always, on Google Hangouts and via email if you have questions. By all means, bother me all day. I will help you out. Hope you guys have a good day, and take care. Easter's coming up.